So this is part 2, or part B, of 3.5, graphing rational functions. So in an earlier, in the part A, we talked about vertical asymptotes and horizontal asymptotes. So this is a list that tells us to find the asymptotes of a rational function. And of course we always imagine that our rational function has been reduced to its lowest terms. When they put something in italics, it's really important. Let me give you just a really quick example of what that means. I'll come back to that just in a second. So let's define a rational function. I'm going to give you a rational function that's not reduced to its lowest terms. So this is not reduced to its lowest terms, and I'm just going to say that's px over qx. And put that closing parentheses there, because we can factor px. Px is just the difference of squares factorization. That's x minus 5 times x plus 5. And then it's divided by x minus 5 times x minus 3. Now, just like when we reduce fractions to their simplest terms, we cancel out any factor that is in both the numerator and the denominator. So now, expressing f of x in its lowest terms, it's simply x plus 5 over x minus 3. So this is f of x in its lowest terms. This here is f of x not in its lowest terms. So I just wanted to make sure you understood that, because our theorems require that our rational function be reduced to its lowest terms. So if you're doing this and you're not getting things right, that may be because the original function is not reduced to its lowest terms. So let's go back to our check. So to find any vertical asymptote, we actually did this. We set the denominator equal to 0 and solve for x. So if the denominator is a constant function, like the denominator is 2 or 10, there's nothing to do. There are no vertical asymptotes. But if the denominator is a non-constant polynomial, then we set that polynomial equal to 0 and we solve for x. And the only way we can do that right now is to factor the polynomial if it's not already factored, and we solve for x. And then for each x that makes the denominator 0, the line for each value of x that makes the denominator equal to 0, the line x equals a, where a is a value that makes the denominator 0, is a vertical asymptote. So basically, vertical asymptotes are pretty easy. Other asymptotes. So here we have 3 cases. So remember here, the thing to remember is that we're dealing with rational functions. And rational functions are defined as ratios of polynomials. So f of x is equal to p of x over q of x. And every polynomial has a degree. The degree of a polynomial is the degree of the highest term. So here's our case A. If the numerator has lesser degree than the denominator, then there is a single horizontal asymptote at y is equal to 0. So when we considered f of x is equal to 1 over x, well, p of x is equal to 1, and q of x is equal to x. P of x has degree 0, and q of x has degree 1. Hold on, I'm going to check. It's Halloween-ish, and I hear noises in my bedroom. Don't know what it was, but it wasn't a monster or anything else. Actually, the couple that live next door have been having domestic disputes, and I hear a lot of door slamming and stuff. At any rate, sorry about normally I would just pause it, but when I pause something and have to snip it out and snip this back on it, it takes forever, and I just don't feel like doing it. So anyway, we're back. So the degree here is 0, and the degree of q of x is 1. 0 is exactly 1 less than 1, so it has a horizontal asymptote at x is equal to 0. Now this is a good example. Now let's do m of x. M of x is equal to 1 over x plus 1 squared. Well, our p of x in this case is the constant polynomial, and it has degree 0. What is the degree of q of x? Well, we can see that x plus 1 squared has degree 2. If you don't believe me, then you can just expand x plus 1 squared to get x squared plus 2x plus 1 has degree 2. So that we don't know exactly what what type of other asymptote it is, because if the numerator has lesser degree than the denominator, then there is a horizontal. So we do know in this particular case that the degree 0 is less than 2, so this is horizontal. But we discovered that if we do g of x is equal to 1 over x plus 2 squared minus 1, notice in that case our horizontal asymptote was is y is equal to minus 1. And that's not the same as y is equal to 0. So what gives? So let's look at that. I was tempted to do this examination when we dealt with it, but let's look at it again. I think it was g of x. So g of x is equal to 1 over x plus 2 squared minus 1. Well, technically, this is not in the form of p of x over q of x, right? So what we need to do is find a common denominator. So I'm going to write, we only really have one non-trivial denominator, and it's x plus 2 squared. And I'm going to write 1 as x plus 2 squared divided by x plus 2 squared. So g of x is really equal to 1 minus x plus 2 squared over x plus 2 squared. So let's simplify our numerator. That's equal to 1 minus x squared plus 4x plus 4 over x plus 2 squared. Yeah, you're glad I didn't do this last time, right? It's really not bad, but the simplification, once you're just grasping concepts. So now let's simplify again the numerator. That's minus x squared minus 4x, and then this is plus 1 minus 4 all over again, x plus 2 squared. So our final answer is minus x squared minus 4x minus 3 over x plus 2 squared. So our degree of px and our degree of qx is both equal to degree 2. They're the same. So that takes us to our next case. So if the numerator and denominator have the same degree as they do here, and the function is of the form f of x, we don't have it in that form yet, but we're going to convert it into that form, then the horizontal asymptote has equation y is equal to an over bn. So let's actually take it to that form. So all I have to do is expand the bottom, x plus 2 squared, and that is x squared plus 4x plus 4. So remember, a in x squared plus a in minus 1 x plus a, I guess that would be a2 x squared plus a1 x squared. If I could just get this right, I would be happy. a1x plus a0, those are the coefficients. And down here on the bottom, it's degree 2 polynomial, we have b2 x squared plus b1 x plus b naught. So let's put this front and center, okay? So my value of a2, which is the leading coefficient, is minus 1. My value of b2, which is the leading coefficient down here, is equal to 1. So the line y is equal to a2, hold this better, a2 over b2 is equal to minus 1 over 1 is equal to minus 1. And indeed, by easier methods, we discovered that y is equal to minus 1 was the horizontal asymptote. But now we're literally using this. So let's look at this again and discuss it. So if the numerator and denominator have the same degree, you expand them out. You have normally you never take factored forms and expand them. That means multiply them out. So you get the sum. Well, in this case you have to. Find the leading coefficient of the polynomial in the numerator and the leading coefficient of the polynomial in the denominator. Then the line y is equal to the an over bn, the leading coefficient in the numerator divided by the leading coefficient in the denominator, is another horizontal asymptote. And then our final brand new asymptote, if the numerator is of degree exactly 1 more than the denominator, then there will be an oblique slanted asymptote. That means it's the equation of a line that has a slope that is greater than 0 or less than 0. It's a non-zero slope. It's a slanted line, not a horizontal line and not a vertical line. Remember, vertical lines don't have defined slopes. So to find it, divide the numerator by the denominator and disregard the remainder. So that's going to require polynomial division. Set the rest of the quotient equal to y to obtain the equation of the asymptote. Here's another important note. A lot of stuff to take in, right? The graph of any rational function cannot intersect any of its vertical asymptotes. That means once you've found vertical asymptotes, the graph never crosses them, ever, ever, ever. And in addition, there can be at most one other horizontal or slanted asymptote, at most one. And the graph may intersect that asymptote. So that's how you have to be careful. The graph could intersect it. You don't always know. So this is a really important page to have in your notes. So here we have 3 graphs. And let's go ahead and use everything we can to find out about the asymptotes. Somewhere here I have that. Oh, wow. Yeah, well, that's because. Let me just get it down here, and then I can see. Good enough. So, our first function, let me write it down. Yeah, I think I keep hearing weird banging noises next door. And yeah, I'm going to actually watch a scary movie after this. Can't wait. Domestic quarrels. It's really annoying sometimes. So it's x plus 1. If you fight all the time, why be in a relationship? That's my view. So let's do it. So we want to first find vertical. So what do? We take the denominator and we set 2x minus 1 times x plus 3. We set it equal to 0. Then we use the zero product theorem. That implies 2x minus 1 is equal to 0, or x plus 3 is equal to 0. Well, the first equation implies x is equal to 1/2. You should be able to solve these in your head at this point. The second implies x is equal to minus 3. So the conclusion is there are 2 vertical asymptotes. And the equations of those 2 vertical lines are x is equal to 1/2 and x is equal to minus 3. So, what is the degree of our rational equation? Remember, by definition, it's the ratio of 2 polynomials. Well, the degree of p of x is the degree 1 polynomial. And the degree of q of x, if I multiply this out, you don't have to worry about it. The degree of 2, the product of 2 linear factors, is always degree 2. You just go right ahead and multiply it out, and you'll find. So this says, if the numerator has lesser degree than the denominator, then there is a horizontal asymptote at y is equal to 0. So we found 1, and the next one, horizontal at y is equal to 0. So let me jot this down really fast. Oh, I don't have to. Let's actually see what that looks like. Let's actually see what it looks like. Since the numerator and denominator are factored, we know the theorem holds because they're reduced in their lowest form. So let's go over to GeoGebra, and let's do some lines. X is equal to 1/2. That's going to be one vertical. And then our other was x is equal to -3. That's another vertical. And then we have a horizontal at y is equal to 0. So now let's actually plot our function. So we're going to do x plus 1, x plus 1 divided by 2x minus 1 times, not done yet, x plus 3. Yeah, kind of cool, right? We can see that our functions right here are vertical asymptotes, and our line our graph never ever crosses those. But we also see that we have at most one horizontal, and if x is less than -3, it does not cross the horizontal asymptote. If x is greater than 1/2, it doesn't cross the horizontal asymptote. But between -3 and 1/2, it does. So this is a perfect example of what we learned right here. The graph cannot intersect any vertical asymptote. There can be at most one other non-vertical asymptote, and the graph may intersect that asymptote, and it does actually between -3 and 1. Pretty cool. So let's do the next one. 2x plus 1 and x minus 3. Yeah, I just kind of want to have this right here for us to reference. That's the reason I have better. I'm using the mouse. It's much better to have my magic pen. That's probably good. So our second one, so this is actually problem 4b. We have the following: 2x plus 1 over x minus 3. It's fully simplified, right? I cannot factor. 2x plus 1 is prime, x minus 3 is prime. So let's do vertical. And all I have to do is set x minus 3 equal to 0, and that gives me x is equal to 3. So that right there is the equation of my one vertical asymptote. Now the degree of my polynomials, the degree of my polynomial in the numerator is degree 1. And the degree of my q of x, my polynomial in the denominator, is also degree 1. So they have the same degree. So we're looking at the going with what they have. Let's look at other asymptotes. So the numerator doesn't have lesser degree than the denominator. They have the same degree. So the leading coefficient on the numerator is 2. And the leading coefficient on the denominator is 1. So the line y is equal to 2 is a horizontal. So let's check it. Let's go over to GeoGebra and check. So we discovered that we have x is equal to 3. We have one vertical asymptote. Then we have y is equal to 2 is our horizontal. I didn't type in. Y is equal to 2 is our horizontal. So I'll center the graph kind of there. So let's actually look at our graph. It's 2x plus 1 divided by x minus 3. Interesting. So again, we see that in this case there's only one vertical asymptote, and always we never have the graph ever cross it, and we have only one horizontal asymptote, and we can only have one, and the graph in this case does not cross it. So sometimes it does and sometimes it doesn't. So far not so bad. I just looked, my other video was 58 minutes, and I know this one's going to be more like 45 by the time it's all done. So that's the reason I split them up. You can take a break and kind of get used to each one. Although we don't have too many problems for this particular one. So this is 4c. So we have x squared plus 1 over x minus 2. So let's do vertical. Vertical's super simple, right? Especially in this case, I just said x minus 2 is equal to 0. I mean, if it weren't factored, we'd have to factor it. That gives x is equal to 2 is our one vertical asymptote. But now, if we think about this, that's px over qx. Px is a degree 2 polynomial, and qx is a degree 1 polynomial. So if the numerator, we have to go to the very bottom condition. If the numerator is of degree exactly 1, more than the denominator, then there will be an oblique or slanted asymptote. So to find it, we divide the numerator by the denominator and disregard the remainder. Set the rest of the quotient, that's what we get on the result of division, and after disregarding the remainder, equal to y. So here we go. This is going to be an easy one, especially after some of the divisions I did in the last optional one. So we're going to divide the numerator by the denominator. So the x squared plus 1 is our numerator. And remember, I have to put a 0x term in there because I have to have a degree 2, a degree 1, and a degree 0. And I'm dividing it by x minus 2. Well, x squared divided by x is x. So x times x minus 2 is x squared minus 2x. So what do? We change the signs. That becomes minus, that becomes plus, and we add. And I get 0 plus 2x. And of course, this is always just 0 plus 1. So 2x divided by x is 2. So that's plus 2. So 2 times x minus 2 is 2x minus 4. So we are going to have a remainder. We are definitely going to have a remainder. So we go ahead and we change our signs. That becomes a minus, and that becomes a plus. And that's our remainder is 5. Remainder is equal to 5. But it says to disregard the remainder and set the quotient. So the quotient is this right here. That's what we got. So we set the quotient equal to y. So y is equal to x plus 2. And that's a line of slope 1 with y-intercept at 2. So when we plot this, we'll actually see an oblique asymptote. And this is going to be a good one for us to look at. So we have one vertical at x is equal to 2. And then we have an oblique at y is equal to x plus 2. So wow, that's kind of interesting. So this is going to be an asymptote. Let's see what it's going to look like. So what we have is x squared plus 1 divided by x minus 2. Wow, look at that. So right here, a vertical asymptote. Graph never crosses it. And as x gets larger, f of x gets closer and closer to that vertical line. As x gets smaller, well actually larger in absolute value in the negative direction, then f of x approaches that line. So that's a good example, a really good example. So now we're getting there. A whole bunch of steps. So a comprehensive graph of a rational function will show all of the following characteristics. The x and the y-intercepts. So you have to remember how to find the x-intercept. You set the equation equal to 0 and solve for x. The y-intercepts, you evaluate the function at 0. F of 0 is the y value of the intercept. You find all asymptotes, vertical, horizontal, and oblique. You want to find the point at which the graph intersects its non-vertical asymptote. So we'll go back and we'll deal with that one. I forgot that one. And then you define the behavior of the function on each domain interval determined by the vertical asymptotes. So let me go back. Oh, well, it doesn't tell us how to do that. So we go back. I thought it was in that list. So the point at which the graph intersects its non-vertical asymptote, if there is any such point. So let me talk about that right there. So if a graph intersects that, as in this case, And what we do is the graph is f of x is equal to, what was it, x squared plus 1 over x minus 2. So I want to know if any value of f of x is equal to a point on that line. So what I would do in this case is you set the function x squared plus 1 over x minus 2 to x plus 2, and you solve. Now, I just want to show you how this would go. We're going to do easier ones. So what we do is we clear denominators. So I would multiply both sides of that equation by x minus 2. So let's go ahead and do this. X squared plus 1 is equal to x plus 2 times x minus 2 is x squared minus 4, because that's just the difference of perfect square factorization. Now we solve for x. I notice that the x squared terms cancel. If I move the x squared terms to one side and the constants to the other, I get 0 is equal to minus 5. So if we go all the way back to the first of the class, that means no solution. So what that tells us in this particular case is that the graph does not intersect at any point in this case, the slanted asymptote. And you can see that if you look at it. It never ever crosses it. And we'll do one of those. So that's what you do. So let me just write it down in case you're taking notes. To determine whether f of x is equal to, and it's going to be a rational function, so by definition it's p of x over q of x, intersects, that means crosses, any, here we go, it has to be non-vertical asymptote, because we already know that it never crosses the vertical ones. Set the equation of the non-vertical asymptote equal to f of x, clear denominators, and solve for x. So that's what we did here. That was the equation of our slanted asymptote. I set it equal to f of x. I cleared denominators and I solved for x. And if there is no solution, never crosses. If x is a solution, then the point x, f of x, is where f of x crosses. Remember, f of x is our rational function. And if so once you do this and you solve the equation for x, if x is a solution, over here we didn't have a solution, but if a solution exists, then the point x comma f of x is a solution. So if y is equal to 0 and we solve blah blah blah, I think we'll get an example. I don't want to make one up. If you try to make one up in this particular class, it can just be a nightmare. So let's go on down. So this is, I think, our only challenge is just to do this one problem. So I've got to sketch it down. No, I don't have to sketch it down. So let's go back over and we will, I am going to do a new one, a new canvas, because I want to copy this over. Sometimes I have to start it over. I don't know why. Looking forward to Halloween? Actually, I'm just going to sit out a big, huge bowl of candy and some hand sanitizer. Are you kidding me? And some hand sanitizer. And just let people come and help themselves. That's what I'm planning on doing. Although I'm already into the candy. God help me. Okay, let's go. So this is 5. You're going to see this one. This is 5. And that's it. So f of x is equal to x plus 1 over 2x squared plus 5x minus 3. So let's find all of the x-intercepts and the y-intercepts. So let's do this bulletin at a time. Find x-intercept. That occurs when f of x is equal to 0. So we solve 0 is equal to x plus 1 over 2x squared plus 5x minus. So if I clear the denominators, I'm going to literally, well, what should we do first? Actually, let me do this full on. Before we do anything, I have to make sure that f of x is in reduced form. So the only thing we have to do is we have to see if 2x squared plus 5x minus 3 can be factored. If it's prime, then it's absolutely in reduced form. And even if it's not prime, it could still be in its reduced form. So this is 2x squared minus 3. That's helpful. And 5x. So minus 3 can only come about by having minus 1 and 3 or 1 and minus 3. So I'm going to put x here and 2x here. So x times 2x is 2x squared. Minus 1 times 3 is minus 3. So x times minus 1 is minus x. 2x times 3 is 6x. Wow. So f of x, I'm glad we did that, that's going to help us out, is equal to x plus 1 divided by the factorization x plus 3 times 2x minus 1. So f of x is in reduced form. So I want this space, so I'm going to go ahead and erase this factorization. Of course, I don't worry about it because you can pause the video and come back. So we've checked that. So now that I've done that, I'm going to tell you the easy way to find the X-intercept. Set the denominator equal to 0 to find the X-intercept. So our denominator is x plus 1. So that gives x is equal to minus 1. So at the point x, f of minus 1, we have our X-intercept. So notice that I should have probably found the domain here, but I know that f of minus 1 is equal to let's just find the value of f of minus 1. And I know that's equal to 0. So at minus 1 and 0, that is the point where the function crosses the x-axis or touches the x-axis and bounces off. Sorry about that. I was already thinking about there is no need to find x f of minus x because I already found it. I am looking for, remember, the x-intercept is some point c and 0, and we already found what the value of c is. It's minus 1. So this is the X-intercept. So now let's do the Y-intercept. So the Y-intercept is found by evaluating f of 0. And it's the point 0, f of 0. So f of 0 is equal to 0 plus 1 over 0 plus 3. 2 times 0 is 0, so minus 1. So that's equal to 1 times 3 times minus 1 is equal to minus 1/3. So the point 0 minus 1/3 is the Y-intercept. So let's actually, I'm going to kind of put little thingies here so we can find this information. Let's go ahead and graph those 2 points on GeoGebra, because that's what we're going to be doing. So I'm going to start a brand new one. So the point 0 and minus 1 divided by 3 is the x, is the y-intercept. And then the point minus 1 and 0 was the x-intercept. So we've got those plotted. So now what we want to do is we want to find all asymptotes, vertical, horizontal, or oblique. So notice that the degree of the denominator is degree 1, and the degree of the, it's Saturday night, people. The degree of the numerator is 1, the degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. So what does that tell us? That tells us we have a horizontal at y is equal to 0. Vertical ones, we set the denominator equal to 0. So we set x plus 3 times 2x minus 1 equals to 0. That gives us x is equal to minus 3, and x is equal to 1/2. So let's add those to our graph. Horizontal is y is equal to 0. And vertical is x is equal to 1/2. And then the other one was x is equal to minus 3. So we know it's going to be doing some weird stuff. We know it's going to be, these are our vertical asymptotes, so they can't cross. So whatever goes on between these 2 points, it's never going to cross there. So let's go on and let's see what else we're supposed to do. So we found this one, and we found the vertical and the horizontal. The point at which the graph intersects its non-vertical asymptote. This is what we do. We set, this is what we were just saying we should do. We have our horizontal asymptote equal to 0, so we set f of x equal to 0. And f of x is x plus 1 over x plus 3 times 2x minus 1. But we already discovered that x equals minus 1 is a solution. So we find the value of minus 1, and we already know it crosses at that point, and indeed we have already indicated that point. So it is going to cross, so we know right now that it is going to cross the vertical, it's going to cross the horizontal asymptote right there. So we will, I just started Teams. I'm just going to give up. No, I'm not. We're going to go through this for the end of the night. So we conclude crosses horizontal at minus 1 and 0. Okay, so we've figured out that one. The behavior of the function on each domain interval determined by the vertical asymptotes and X-intercepts. So we already found that our X-intercept is minus 1 and 0. So what we do here is we come down here and let's look at our function. This is the kind of weird stuff. Our function is equal to x plus 1, and the factored form of the denominator is x plus 3 2x minus 1. So we want to find where is the numerator is 0 at x is equal to minus 1. Denominator is 0 at the points x equals, I'm going to do a little bit better, equals there, x equals minus 3, or x is equal to minus 1/2. So what we're going to do is I'm going to write 2 lines. The top we will say stands for the numerator. These are 2 number lines, okay? And the bottom is going to stand for the denominator. And what I want to do is I want to put 3 points there. You don't have to have a 0, it doesn't matter, but I am going to add 0. Oh, no. Minus 1, minus 1/2, and minus 3. So this is going to be 0. This is going to be minus 1/2. Oh, it's actually at 1/2. So let me just relabel these, because all we need is conceptual. So we discovered minus 3 and plus 1/2 as where our vertical asymptotes are. So I'm going to call this is going to be 0. This is going to be 1/2. This is going to be minus 1. And this is going to be minus 3. Now here we do something really odd. We take our denominator, x plus 1 is greater than 0. So we solve that equation. So that implies x is greater than minus 1/2. So for the denominator, if x is greater than minus 1/2, it's positive. On the other hand, if x is less than 1/2, it's negative. So these are little minus signs that mean they're negative. At the value of x is equal to minus 1, it's 0. Now let's do the same thing for each of our linear factors. Let's solve x plus 3 is greater than 0. Well, that implies x is greater than minus 3. So I'm going to do another thing here. If x is greater than minus 3, it's positive. And if x is less than minus 3, it's negative. Now I've got to do the other thing for the other linear factor. 2x minus 1 is greater than 0. Well, that implies 2x is greater than 1, which implies x is greater than 1/2. So again, if x is greater than 1/2, this is down here at the denominator, then that factor is positive. If x is less than 1/2, then it's negative. So now we start looking. Let's look at intervals. So from all of this now, I want to find the intervals in which f of x is positive or negative. So if I start down here and go to minus infinity to minus 3, I have a negative times a negative. So down here, we have a negative times a negative, which is a positive, and we have a negative multiplied by that. So we have 3 positive, so that means over this interval it's negative. Now let's look at the interval from minus 3 to minus 1. I have a negative and a negative, which is a positive, which is then multiplied by a positive. So over this interval, it is positive. Now let's look over the interval from minus 1 to, we don't care about the 0 there, minus 1 to 1/2. So the 0 is just there for reference, okay? So from minus 1 to 1/2, I have a positive times a positive, which is a positive, times a negative, which is a negative. And then let's look at the final interval from minus 1/2 to infinity. I have a positive times a positive times a positive, so it is positive. So I start out negative, then I go to positive, then I go to negative, and then I go to positive. So when I actually plot this, we'll actually see how interesting it is. So over here on GeoGebra, in this section it's negative, and that's an asymptote. So it has to get really close to the x-axis, and then it's always going to stay negative, so it's going to stay underneath, so it's going to go down that way. In between minus 3 and 1, it's positive. So since this is an asymptote, it's going to come down, it's going to approach that, come down, cross here, and then between minus, what is that? Minus 1 and 1/2, it's going to go negative, and it's going to cross over there and then approach that going down. And over here it's always positive, so we're going to see this like that. I wish I could draw on this, but let's just see what it looks like by plotting it. X plus 1, that equals 1, plus 1, divided by x plus 1 divided by x plus 3 times 2x minus 1. And right there is our function, just as I tried to describe, and you can see it. So we got through it. That's all of the stuff you have to put together. All of that stuff right there. So you just complete the sketch. In this case, if I had been able to draw on my GeoGebra screen, you could have seen me do that, but you'll get the practice of this. So this is the very last part of 3.5, and it's done and it's over, and I'm ready for popcorn and a scary movie.